Okay, I think we can begin. 260 is probably the usual number, I guess. All right, welcome to week 7 of AI504. So far we've covered, what did we cover? We covered, except for the classical neural network, classical models, we've covered the basic neural network, a basic neural network, and then autoencoder, variational autoencoder, and then GAN, so which are all like, generative models actually. Except, autoencoder is actually just a compression decompression model, but then VAE GAN, both generative models, and then as I said, the third generative model, which will be the diffusion model, we will cover that at the end of the semester. So this week now we're covering more of a foundational architecture such as convolutional neural network this week, and then following that will be word-to-vec. After this we'll be covering word-to-vec and subword encoding. Then we'll move on to RNNs, attentions, transformers, and then a couple more transformer related works. Then I guess will come diffusion model and then the graph neural networks. So if you have any questions so far before we move on to the foundational architectures, questions, any questions? You can ask questions anytime you want. I'll just start with the topics today. And by the way, the announcements about project number 1 will be shared by the TA this Thursday, and then as I said, there will be 2 weeks period before the deadline. So, and it would be relatively a simple first project, which will be generating people's faces using GAN. Actually, it will be a deep convolutional GAN. It's not just basic GAN that you guys studied last week, which was based on simple feed-forward network, but it'll be a GAN based on CNNs. So since you're covering CNN today, it won't be that hard actually. There are a lot of DC GANs or GAN variants out there, so you can use any of them to generate faces and then satisfy the FID criteria. Right, so today's topic, CNNs. So for the first time, we'll be talking about CNNs formally, about all these factors of CNNs. And then we'll be talking about a little bit of a BatchNorm and Dropout. Well, more about, Dropout is a relatively easy concept, but BatchNorm, we will delve into BatchNorm, layer norm, and instance norm, and that kind of stuff. And if we have time, we'll be talking about the various architectures, the historical history is a bit of a strong word, but well-known architectures like VGG, Inception, ResNet, and so on and so forth. Was there a question? Okay, true something. Yeah, please check yourselves in. So CNN. Well, it is said that the CNN kind of mimics how humans' visual cortex works in the human brain. So when the eye, which is the photoreceptor, 이제 광자를 받아들이는 수신기죠, 눈은. So there's a photoreceptor, which is your eye, and then because the photons hit the receptor in your eye, and then the electric signals will be fired. So it's a neuron. Basically, we talked about how neurons can fire electric signals and then propagate signals over to another neuron, right? So there's like a spark, electric signal like sparking here, and then it will be propagating into the human brains, and then it is said that it follows this path, right here, and as you go higher, or as you go further along the chain, the electric signals become more like abstract and more semantic. So as you can see here, in the lower visual cortex here in V1, you see edges. Well, I'm not sure how scientists found this out, but you see, your brain sees edges and lines, which are the very basic unit of objects or meaning of the world. And then in the V2, which is the next process or next step in your brain, it'll be start recognizing shapes. So shapes are actually a composition of edges and lines. So edges and lines compose shape, and then shapes compose objects, and then object composes faces, or actually all the other things. All the things that you can recognize, like cars and dogs and cats and people and people faces and all that kind of stuff. So that will be happening here when the very in the very center of your brain. So inspired by this this process, inspired by this kind of like neural architecture or brain architecture, CNN is born. So CNN, the very first CNN or convolutional neural network that was proposed was back in 1998 by, people that you've heard of, Yann LeCun, Leon Bateau, Yoshio Bengio. Not sure the first name of this person, but anyway, these people were doing neural network stuff even like how many years ago? This is like 24 years ago, right? 24, 25 years ago. So, they were back there when the history started. And they're still here even now, so which is pretty amazing actually to think about it. So it's called Linnet, probably after the name LeCun. So Linnet 5, which has 5 layers, and it was gradient-based learning applied for document recognition. So there's a pixel-based information here, and then just like how humans recognize objects through a chain of visual perception, like here, V1, V2, V4, IT. You have a chain of transformations, chain of transformation, or I would say chain of transformations, where pixel-based information is transformed into, hopefully, something like edges, shapes, objects, and number or alphabet. This is alphabet. So there's, hopefully here, it is recognizing edges. Here it is recognizing shape. Shape. Here it is recognizing objects. And then here is recognizing the alphabet. And then there's a final output, which is from A to like Z, right? So that is what's happening here, hopefully. And so this whole, and in this chain of transformation, there are steps called convolution, sampling, and convolution and sampling. So we'll talk about that. Further question again? Okay, yeah. Attendance. And then, so that was 1998. And then how many years later? 14 years later came AlexNet. So AlexNet 2012, which actually gave birth to the modern era of deep learning. So this architecture is the one that actually got a like a quantum jump of a performance on ImageNet challenge, basically, and done by Alex Krichevsky, Ilya Suskiver, who's now in OpenAI, Geoffrey Hinton, the professor. And you can see it's a bit of a complicated architecture compared to Linnet here. So it has like two streams of signal propagation, and then at the end it is concatenated or somehow combined, and then you're left with 1,000 classes, which is the number of classes in ImageNet. And it has a lot of, it has max pooling, non-local response normalization, which is not usually used anymore. We'll talk about the architecture if we have time. Then, so that was 2012, and now, modern ConvNets can do a lot of different things. Classification, retrieving, similar-looking objects or semantically similar objects, and then, object detection, semantic segmentation, like pixel segmentation, like here, and captioning. Well, actually, captioning is done. Traditionally, captioning was done by via a combination of ConvNet and RNN. Well, these days, captioning is done by just transformers these days, because we now have like VIT, vision transformers. So ConvNets are losing its place slowly, but gradually, because transformers are taking over its place in simple image processing these days. Even like ImageNet recognition can be done by vision transformers. So ConvNets are losing its merit a little bit, but still, it's a very efficient architecture compared to transformers. CNN requires way less number of parameters, and it shows like very nice performance. It trains faster. It has a lot of good properties. And style transfers. We talked about style transfers. It's like CycleGAN and StarGAN and that kind of stuff. So this is the end of a very simple introduction of CNNs, and we'll start with the very basics. And all the materials are actually borrowed from 231N, if I remember correctly, which is the deep learning for visual image processing or computer vision from Stanford, which is a very, very nice course. So I'm pretty sure a lot of you actually went through it, but so you can think of it as a recap. So why is CNN required to begin with? Why is it so different from linear linear feed for linear networks, or MLPs to be another name? So we talked about MLPs, well, feed for neural network, right? So which is if you imagine you have a 32 by 32 by 3 image, so 32 by 32 by 3 is like, it's a width, height and width, and there's like a three-dimensional channel RGB. So this is 3. This is 3. So this is your input. And suppose that you flatten it like this. So now you have a flattened pixel information, which is 3072 by 1. And then suppose you want to do a classification. Maybe it's like a digit, like 0 to 9, and you want to classify it by using feed for a neural network, just a simple linear transformation. So you have W matrix, which transforms your 30,000 input into a 10-dimensional input. So there's like 0, 1, 2, 3, all the way to 9, right? And so what you need is a transformation from 3000 to 10. So you have a 10 by 3000 matrix basically. So you require 30K learnable parameters. So, and hopefully, and then you hope it to work. Actually, that's it. And you can actually add a value function in front of it and that kind of stuff. But this is how you would go about doing a classification of 3000 pixel values. But if you think about it, this whole class, there are a number of classes, and this, in order to arrive at this number, what you do is you just simply, so if you draw the W here, W would look like this, 10 by 3000, right? 10 by 3000. What you do is you have a 1 by 3000 input, so it's a 3000 input, and you do a inner product between this one and this column, this one and this column, this one and this column, one at a time. And that's how you arrive at numbers here, the first, here on the second, third, fourth, all the way to 10th. That's what the numbers really mean here. It's that what you do is you simply just do an inner product between a input and just a column, one of the columns in this. Actually, I'm sorry. This is a wrong picture. Very sorry. It's actually this way. Obviously. So you do on your product between this one and the first row, the second row, third row, all the way to the 10th row. And that corresponds to the first row, first column, first dimension, second dimension, third dimension, all the way to the 10th dimension. So it's a pretty, if you think about it, it's a pretty stupid way of arriving at a number, because all you do is just do a simple inner product, and that's it. Compared to that, CNN is a bit different. So CNN it preserves the spatial structure. It's written right here, because you're given a 2-dimensional input. It's a 3-dimensional input because you have 3 channels. There's R and G and B. But just think, if you just ignore the number of color channels, you're given a 2-dimensional input. There's a height and width, and you still want to somehow use that for arriving at the final conclusion, final class prediction, right? So that's where convolution comes in. So if you think about this one, this has nothing to do with spatial structure, because you've flattened it. So everything is just, everything is just mushed together. Like this is up here, this is all like width, this is all height, this is width and height, and you repeat this for 3 times because there's R and G and B channels probably. So it's a very stupid way of doing a signal processing given 2-dimensional input. Now you want to preserve the spatial architecture. So suppose that you have something called filters, or sometimes it's called kernels. And has a dimensionality of 5 by 5 by 3. So which means that you have a 5-dimensional height and 5-dimensional width and 3-dimensional input channel. 3-dimensional depth or channel again. The reason that there's three-dimensional channel is because there's three-dimensional channel in the input, so you need three-dimensional depth for your kernel as well. And the 5x5, this number 5 can actually be 3x3, could be 7x7, could be 9x9. It's up to you, but just for sake of argument, we're using 5x5 as an example. And then taking this the object called filter, or we're taking this filter or kernel, we do something called a operation called convolution. We convolve this filter across the two-dimensional input signal, like so. Well, actually, we haven't gotten there, but so basically, what we do with a single convolutional single operation is that we take the kernel, or we take the filter, and then all we do is we take a inner product between this kernel and the corresponding input signals here, and right here. Well, actually, it's overlap. So, but if you think about like here, because this is a two-dimensional input, there should be a corresponding region. So you have some numbers in your filter. So you have 5x5x3. So there's a 75 numbers, 75 values here inside, like 75 values inside, like 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Corresponding numbers should be here in the pixel value. Some value, some value, some value, some value, some value. Like there would be 5x5x3 values in your input as well. And then what you do is you simply just do an inner product. So you multiply the numbers here. You multiply the numbers, this number with this number. Actually, I should maybe draw it a little bit clearer. There's number here, there's number here, corresponding number. You multiply it. There's another corresponding number here. You multiply it, multiply, and multiply. That's it. And then you do this for the second row, third row, fourth row, fifth row, 5 numbers at a time. You multiply and multiply to the corresponding numbers in your filters all the way, and then you simply just sum them up, sum the multiplication. You have 75 multiplications, right? Because there's 5 by 5, and 3 channels inside, so you have 75 multiplications going on. And then after that, you sum all the numbers, all the multiplied numbers, and then you add a bias, and that's it. So that's why we call it a inner product, taking a dot product between the filter and a small 5x5 chunk of the image. So 70, as I said, 75 dimensional dot product and a bias. So that's it. And then what you do is you move. Was there a question? Okay, I'm just mute everybody. And then you do this across your input like this. So here you start with the very first position, and then you slide to the next position. Next position is, you keep on doing it, and then if you do it across the entire input sample, you will get a following output, which we call an activation map. So if you think about it, you start with 5x5x3. So you start here, let's see, you start here. And then you move across by one pixel, which would be here. Like you start with this, and then the next time you move across, so you will be here. It'll be here, and then you move across 1 pixel here. Like this. So if you think about it, there are 32 pixels here, and if you move across, if you slide your five-dimensional kernel or 5-dimensional filter 1 pixel at a time, you will get 28 out of it, right? If you think about it, you'll get 28 out of it, because each time you slide, you get 1 pixel. So for the first spot, you get 1 pixel value out, because you're doing an inner product plus bias. And then in the second slot here, in the red slot, you get 1 pixel out. 1 scalar value out. In the third position, this black region, you get 1 scalar value out. And if you go all the way to the final position here, you get another 1 pixel out. So there will be how many pixels? There will be, there 1 scalar value out. So how many scalar values will you get out of the first slide that you will get 28 scalar values. And you can do this over to you move on to the next row, which is 1 pixel down. So you start again here, move across all the way. You slide down again 1 pixel, you go across all the way. So you get 28 rows in result. So you see how this is moving, right? So convolving, which is basically sliding over your input signal, you get a 28 by 28 by 1, because you get one scalar value, 1 at a time. So you get 28 by 28 by 1 activation map using what? Only 75 dimensional parameters. You only have 75 parameters for arriving at this activation map. So far, so good, right? If you have another filter, so this is the first filter, which is blue color filter. If you have another filter, which is green color, assuming that there are different numbers in your filters. So as I said, there are 75 basically weight values that you need to learn, 75 parameters that you need to train. So there in the first kernel or first filter, there would have been 75 parameters inside. In the second kernel, there's another 75 parameters inside. And using this kernel, using this filter, you get another activation map, which is differently colored, meaning that there are differently valued, right? Was there a question? What does filters always extend the full depth of the input volume exactly mean? That means that if you have 3 input channels, then your filter should also have 3-dimensional input, three-dimensional depth. If you have, we'll talk about that later, actually. So your kernels or your filters, the depth of your filter is the same as the depth of your input. Hopefully that is clear. Yeah, it means that you can't have 5 by 5 by 2 filter when your input channel is 3. All right. And it can't have 4, it can't have 5. It has to be exactly 3 in order for it to work. All right, moving on. So as I said, different filters give you different activation maps. So if you have here, if you have 6 filters, so you have 5 by 5 by 3, and you have 6 of them, then you'll get 6 activation maps, like here, 6 activation maps. So that's how you transform 32 by 32 by 3 input into a 28 by 28 by 6 output, right? So the output number, the output depth, the number of output depth is determined by how many filters you use. If you had used 8 filters, you would get 8 output depth. If you had used 10 filters, then 10 depth that would be. Right, pretty simple, right? Right, so confident is actually just a sequence of this transformation. For example, you start with a 6 5 by 5 by 3 filters, and you get 6-dimensional 28 by 28 by 6-dimensional output or activation map. And suppose that you have like a ReLU function somewhere. Like after doing this, you have, let's assume that you put the scalar value through the ReLU activation function, or it could be 10H, could be sigmoid, but some activation function. So assuming that you have an activation function after conv ReLU, and then you get this one, and then another conv and ReLU, you get this one, and see how the output activation map changes. So assuming that now you have 10 of 5 by 5 by 6 filters. So there's you pay attention to this number here. This is 6 because the input channel is 6. So that's what Toki asked. If your input channel is 6, your filter has to be 6 depth, has to have 6 depth, so 5 by 5 by 6. And assuming that now you have 10 of them, then you will get 10 depth in your output. And now it's 24 by 24. So you're shrinking by 4 pixels at a time, actually. 32 went to 28. 28 went to 24. And you can continue doing this again and again and again. Now, the next time it'll be 20 by 20. It'll be 20 by 20 by something, 20 by 20, 20 by 20 by some depth. And then it'll be 16 by 16 by some depth, so on and so forth. So that's what basically a convnet is. It's just a chain of convolutional operation involving some number of kernels or some number of filters and also non-activation functions. nonlinear activation functions. Right, so something about receptive field. So what happens when you keep on doing this kind of convolution, chain of convolution, one after the other? So suppose that you have 3 convolutions, assuming that, okay, so we start with 7 by 7. 7 by 7. Forget about the input channels. You just have one channel and 7 by 7 width and depth. And you're doing convolution with 3 by 3 filters. Again, let's assume that you have only one filter at a time. So you have 7 by 7 input and you have only one filter at a time. So it's 3 by 3 here. Again, another 3 by 3, and again 3 by 3. So three chains, three iterations, three repetitions of 3 by 3 convolution operations. And what happens here is that at the end, I mean, here we're ignoring the fact that as you do convolution operation, you're losing a dimension, that you're losing spatial structure. I mean, spatial dimensions. Like here, you started with 32, arrive at 28, started at 28, you arrive at 24. We are just ignoring that fact. It's always 7 by 7 by 7 by 7 by 7. But the important thing is what happens when you do 3 by 3 convolutions 3 times in a row, and then you arrive at this final structure. Then one pixel, one scalar value at the final activation map. If you think about how wide the coverage is, you do a backtrace. So this single scalar value at the final activation map is responsible for 3 by 3 spatial information in the previous activation map, right? Because we're using 3 by 3 kernels, so we're doing 3 by 3 we're doing 3 by 3, 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 one at a time, right? So your spatial structure, you're looking at 3 by 3 patch at a time to arrive at a single scalar values in your activation map, right? So you can say that a single scalar value in the final activation map is responsible for 3 by 3 in the previous activation map, right? And one of the 9 scalar values in this previous activation map is again responsible for 3 by 3 patch in the previous activation map. And if you do this again, this single scalar value in the previous activation map is responsible for 3 by 3 patch in the first input value, in the first input signal. So if you think about it, if you apply this chain of logic to the very end, then it means that a single scalar value in the final activation map is responsible for how many? Is responsible for 7. Oh, actually, sorry. So okay, I was confused. This is actually 8 by 8. Sorry about that. So this is 8 by 8. 8 by 8, 8 by 8, 8 by 8, 8 by 8. And again, so what I was saying is that single scalar value in the final activation map is responsible for 7 by 7 patch in your input data, in your input signal. So just by using a chain of 3 by 3s, because we're just using 3 by 3s for this, right? So just by applying 3 by 3 filters, one after the other, 3 times, then your final scalar value will actually cover 7 by 7 as a result. So if you think about, if you wanted to cover a 7 by 7 patch in one go with one single convolution, then what do you need? You need a 7 by 7 filter, right? You need a 7 by 7 filter. Or like in this picture, you can have 3 by 3 times, or 3 repetitions of 3 by 3 filters, which would both eventually give you a 7 by 7 receptive field. So if you think about which is more efficient, 7 by 7 requires how many? 49 parameters. 3 by 3 by 3 requires how many? It requires 27 parameters. So if you wanted to cover 7 by 7 patch, it would have been nice it would be nice to use smaller but more repetitions of smaller filters like this, because this requires smaller number of parameters and it is deeper, so it has more chance of transformation, like non-linear transformations that we saw. If you remember the non-linear transformations of this, this actually, here, and if you remember the structure, how it is, transformed into a nonlinear way, like it is like jiggled and then squiggled and then using a nonlinear activation like this. So the more number of nonlinear layers, nonlinear activation functions, or nonlinear transformation operations, the more powerful your neural network become. It can do more stuff. It can squeeze or extend or rotate your latent space, right? So more depth, 3 depth, is better than a single depth, right? So all in all, it's just always always better to use repetition of smaller filters rather than using one single large filter to cover the same range of same area of receptive field. Question, can you explain this part in Korean? I see. Okay. 그러니까 이제 지금 얘기가 하는 게 지금 이제 다시 시작이 8x8이라고 칩시다. 여기까지 8x8, 시작이 8x8 픽셀이고, 이제 채널은 1이에요. 이제 RGB가 아니면 흑백이라고 치는 거고, 여기다가 우리가 지금 3x3 필터를 3번 연속으로 거는 거예요. 그래서 지금 3x3 한번 하고, 3x3 한번 하고, 3x3 한번 하는 건데, 원래 3x3을 하면은 얘처럼 이제 픽셀이 줄어야 되고, 얘는 이제 5x5니까 32가 28로 줄고, 28이 24로 줄었는데, 3x3을 하면 32가 30으로 줄고, 30이 28로 줄고, 하여튼 이게 줄어야 되거든요. 근데 그냥 편의 이상 안 준다고 치는 겁니다. 안 준다고. 그냥 8x8을 계속 칩시다. 8x8을 계속 치고, 그럼 이제 무슨 일이 생기느냐? 3x3을 계속 이제 컨볼루션을 하면은, 마지막에 액티베이션 맵을 보면, 마지막의 액티베이션 맵의 하나의 밸류, 하나의 스케일러 밸류가 보면은, 얘는 뭐를 담당하고 있냐? 이전 액티베이션 맵의 3x3 패치를 담당하고 있겠죠. 왜냐면은 3x3을 가지고 여기서 쭉 이렇게 3x3, 3x3, 3x3 이렇게 쭉쭉쭉쭉 훑어가지고 하나씩 나왔을 테니까. 그러니까 여기 있는 스케일러 밸류 하나가 여기 있는 3x3을 담당하고 있는 거죠, 지금. 어떻게 보면은. 그리고 다시 이 3x3에 있는 여기 3x3에 있는 밸류, 스케일러 밸류 하나가 다시 또 이전 액티베이션 맵의 3x3을 담당하고 있는 거죠. 여기를. 그리고 똑같이 또 이전 3x3에 또 이 밸류 하나가, 스케일러 밸류 하나가 또 첫 인풋의 3x3을 담당하고 있는 거고. 그래서 그걸 계속 이제 연계를 해서 생각해 보면은 마지막 액티베이션 맵의 마지막 액티베이션의 스케일러 밸류 하나는 시작 인풋 시그널의 7x7을 담당하고 있는 건 똑같다는 겁니다. 7x7을 이만큼 담당하고 있는 거죠. 그런데 다시 그럼 이제 이거 스케일러 밸류 하나가 7x7을 담당하고 있는데, 만약에 우리가 이제 7x7을 담당하게 만들려면 방법이 하나가 더 있죠. 뭐냐면은 여기 써 있듯이 한 번에 7x7 필터를 이용을 하느냐. 그러니까 한 번에 7x7 필터를 이용해도 7x7의 이 패치를 담당할 수 있겠죠. 그게 아니면 여기서처럼 3번의 3x3 필터를 사용을 하느냐. 그러니까 2가지 방법이 있다는 거예요. 둘 다 어쨌든 7x7의 리셉티브 필드를 가진다는 거죠, 결과적으로. 그러니까 이제 한 번에 7x7 필터를 이용하면 한 방에 그냥 7x7 리셉티브 필드를 가져가는 거고, 3개의 3x3 필터를 이용하면 3번의 그 단계를 거쳐서 7x7의 이제 리셉티브 필드를 가지는 거고, 그런 건데, 뭐가 더 낫냐? 그러면 이제 이게 옵션 1번이고, 여기 옵션 1번, 이거 옵션 2번인데, 뭐가 더 낫냐? 일반적으로는 후자가 더 낫다는 겁니다. 왜냐하면은 1번 옵션은 7x7 필터는 49개의 러너블 파라미터가 필요하고, 3개의 3x3 필터는 27개의 러너블 파라미터가 필요하니까 얘가 더 효율적이잖아요. 똑같은 리셉티브 필터 가져갔는데 위에는 49개, 밑에는 27개의 러너블 파라미터만 있으면 되니까 후자가 더 이제 효율적이라는 거고, 그리고 하나 더, 후자는 3개의 레이어를 쌓게 되잖아요. 그럼 이제 레이어를 쌓을수록 더 모델이 강력해지죠. 우리가 예전에 봤던 그 맨 3번째 강의인가에 봤던 이 레이어를 하나 쌓을 때마다 계속해서 그 레이턴 스페이스가 이렇게 쭈그러지고 뭐 돌아가고 뭐 컴프레스 되고 늘어나고 뭐 돌아가고 뭐 그런 작업들을 할 수 있잖아요. 그게 이제 레이어가 늘어날수록 그만한 그 강력한 모델이 되기 때문에 후자가 여러모로 봐도 낫다. 후자가 이제 레이어도 깊고 러너블 파라미터도 적고, 그러니까 이제 한 방에 7x7의 필터를 가져가는 것보다 낫다. 그런 이제 얘기입니다. So this principle was applied the first time I think it was in VGGNet. So AlexNet and ZFNet, which is the 2013 winner of ImageNet Challenge, they didn't really use this principle of using smaller filter, like repetition of smaller filters, but it's starting with VGGNet, so it became way more efficient with no smaller number of parameters compared to the previous ones. Right, so if this is just a like a simple visualization of what's happening in the simple visualization of what happens, what is going on inside different layers of convolution. So if you have like an input signal, and then you have first convolutional layer, second convolutional layer, third convolutional layer, and you try to visualize what each filter is trying to capture, then you can see that's what's being captured is being more and more complex. You start with just simple, like this filter could be only responsible for this single color, like yellow color, bright yellow color, green color, red color. Like each filter is responsible for very simple stuff, or vertical patterns, horizontal patterns, diagonal patterns. And then the second convolution layer, it becomes a bit more complex. Well, I mean, it's hard to interpret what kind of information each filter is responsible for, but is more complex than before, right? Than before. And then in the third layer, even more complex, even more hard to interpret, But that's basically what should be happening. So this is a visualization based on the ZFnet, Zeiler and Fergus. And another example is given this information. So this is what? This is a headlight or a tail light of a car, right? So this is a light here. And if you try to visualize what kind of information the filter is extracting from this piece of information is different for each filter, right? So for this filter, it is capturing this tail light or headlight region pretty strongly. And again, this one as well. Other ones not so sure. Like this, like kind of hard to see what kind of information it is extracting. But this is based on different filters. So the first filter is trying to capture like diagonal pattern here. This filter is trying to capture red region, I guess. So that okay, so kind of makes sense. Because if this filter is responsible for red or orange-ish input signal, and if you look at here, there is some orange-ish input signal here. So that is why this filter gives you a highlighted region here, because this part is orange-ish, right? This part is orange-ish. So basically what's happening. So just a visualization of what each filter will give you. Like each filter has its own responsibility. Some filter is responsible for yellow signals, red signals, blue signals, brown signals, blue signals. Some filters are responsible for diagonal patterns, vertical patterns, horizontal patterns, that kind of stuff. And each filter will give you differently shaped activation maps. So there were different activation maps, 6 activation maps here. Here we're seeing how many? Like 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way to like 24 activation maps, right? Actually, sorry, this is 7 by 28, 24, 30, yeah, 32 activation maps. And each activation map has different meanings or different information. All right. So typically, this is like a complete workable or usable convolutional neural network, which works like this, which has an architecture like this. As I said, we have convolutional neural network, conv operation followed by a ReLU, a nonlinear activation function. Again, conv and ReLU, all the, like how many times? Like 1, 2, 3, 4, 5, 6 repetitions, and some pooling operations in between. So conv and ReLU. So 2 conv and rels. So 2 conv and rels and followed by a pool. Another couple of conv and rels followed by a pool. Couple of conv and rels and followed by a pool. And then after, so at the end, you have a classifier layer here with how many? Like five different classes. So this is pretty much the gist of the convolutional neural network. And all the modern, more like more recent ones, like inception nets and res nets and dense nets and wide nets and that kind of stuff, they're all like variants, extensions of this concept. We haven't talked about pooling operation yet, but we will. Yeah, we will maybe a couple slides later. Right, a closer look at the spatial dimensions. So here, right, I mean, we talked about how 32 by 32 is shrink to 28, right? And that's because we have a 5 by 5 filter sliding across the 32 dimensions, 32 width here, and you are left with 4 pixels smaller, right? So this is a bit more detailed look into that mechanism, that process. Suppose that you have 7 by 7 input, and you're sliding over your 3 by 3 filter, and what you get out of it is a 5 by 5 activation map, because you have 3 by 3 responsible for single value here, another single value here, another single value here, here, and here. So how many scalar values? You get 5 scalar values out of it. So 7 and you do this like again, one pixel lower. Then you do this again. You have 5 scalar values out, and you do this in total 5 times, because you have one pixel, one filter across this row, another filter across this row, again, and again. So you have 5, 5, 5, and 5. So that is how you get 5 by 5 activation map out of 7 by 7. That's what we're going to talk about, right? 7 by 7 by 7 by 7. So that's how you get 5 by 5 output, right? Pretty easy. And if you use larger filter, like 5 by 5 filter, then you would get how many? You would get 3 by 3 output. So it depends on the size of your filter. And if you don't like this happening, if you don't like your activation map being smaller than your input, then you can actually do a little padding. If you had, like extra pads surrounding your input signal, surrounding your input image, one more pixel is here. Basically like this here. If you had a surrounding pads filled with zeros or some mean values or whatever, then if you convolve your filter 3 by 3 filter here, then what would you get? You would get 1 scalar value out, and again scalar value out here. So all the way to here, you would get 7 scalar values out of it, like 1, 2, 3, 4, 5, 6, 7. And since you have 9 height here, you would also get 7. You would get a 7 by 7 output, basically. So that's how you prevent your output activation map being smaller than your input map, by doing a little padding, and that's it. So that's what yeah. Oh, actually, we forgot to talk about the stride, actually. So you don't always have to slide by 1 pixel at a time. You can actually slide by 2 pixels at a time, like this. Like here, you start here, get 1 scalar value out, but here you move you slide by 2 pixels. You slide by 2 pixels, and you get another scalar value out. Again, slide by another 2 pixels. You get 1 scalar value out. So instead of getting 5 by 5 output, you would get 3 by 3 output. Your activation map would be even smaller, because now you're striding by 2. So the size of your activation map is determined by the size of your input signal, and the size of your filter, and the stride of your filter, right? So like at least 3 factors are actually 3 factors are in play here. And yeah, if you try to stride by 3 pixels, what would happen? So you start from here, get 1 scalar value out, and actually, well, the next time you would be here, right? The next time you would be here, and then the next time there's nowhere to go. You're not there. You can't slide by 3 because you're missing a lot of stuff here. So you will end your process will terminate in this patch, and you're even missing out this important pixel information here. So it doesn't really work, because it doesn't fit. You cannot apply 3 by 3 filter on 7 by 7 input with stride 3, because you won't be terminating at beautifully at this patch here. So So you need to pay a little attention to what stride options you have given the size of your input and the size of your filter. Right. Right, so there's a simple equation here where you can determine your output size by, which is your output size is determined by your input dimensions, so which is n, and your filter size, which is f, and the stride of your filter. So, for example, just before what we had 7x7 input with 3x3 filter and stride 1. Then if you plug that numbers into this equation here, then what you would get is this 7, 3, 1. Then you get exactly this. So you get 5x5 output. If you use stride 2, then you arrive at 3x3 filter, 3x3 output. If you try to use stride 3, then you don't get an integer. You get actually a float value, which doesn't actually work. So you can only work with one stride or two, stride 1 or stride 2 with this 7x7 input and 3x3 filter. All right, so far so good, right? So you can use this equation. And there's actually one more. So as I said, you can use paddings to prevent your activation map shrinking. So if you use one dimensional pads, all surrounding your input signal, and if you use 3x3 filter with stride 1, then your output would be, if you follow this equation, now it's 9 because it's 9 by 9 here. This 9 by 9 here. It's 9 minus 3 stride 1 plus 1. That is what? That is 7, right? So just simply by padding by one pixel value surrounding your input signal, you're no longer shrinking your activation map. Right. So there's if you take that equation, take that factor, take that a padding factor into the equation, then you get a new equation, which is like this. So you have n plus 2p. So p being the size of your pad, minus f, and then stride and 1. So you have 4 factors in play now. You have the input size, you have the padding size, you have your filter size, you have the stride size. So 4 things are in play that determines the output, the size of your output activation map. So you're good to go now. So if you use right, so what it's saying here is that if you want to preserve the size of your input if you want to preserve the size of your activation map with differing filter size, you need to have correspondingly different pad sizes. So if you're using 3x3 kernels, you need to pad with 1. If you're using 5x5 kernels, you need to pad with 2. If you're using 7x7 kernel, you need to pad with 3 in order to have the same activation map size as the input size. That's it. That's about it, right? So the question, so if you have input volume 32 by 32 by 3, and you're using 10 5x5 filters with stride 1 and pad 2, what would be your output volume size? Can you calculate using the previous equation? What would it be? Please calculate by yourselves, without turning to the next slide, and then let me know. You can simply just follow this equation. What would you get? Any takers? Shout out the numbers, please. Huh. 2 different numbers, actually. So someone said 30, but well, I guess because we're using stride 1 with pad 2 and 5x5 filters, so your output map shouldn't shrink at all, right? So it's 32 by 32. And since we are using 10 filters, so the output value would be 32 by 32 by 10. So a lot of you got the answers correctly. The answer is 32 by 32 by 10. Right. So if you thought anything else, if you thought 30 by 30 by 10, then you need to recap the things that I just talked about. Right. So far, so good, right? So very easy. Number of parameters in this layer. Actually, it's not that hard because all you need is just calculate how many. Actually, there's a hidden factor here because your filter is not exactly 5 by 5 Your filter is actually 5 by 5 by 3 because your filter's depth should be the same as the depth of your input, which is right here. And so a single filter will require 75 learnable parameters. And since you're using 10 of them, you need to multiply 10 and you get 750 learnable parameters. So that is the number of learnable parameters in this operation or in this layer. 750. Oh, actually, sorry about that. We forgot about the bias. So yeah, a single filter actually has one bias. So I forgot about that. Sorry about that. 76 times 10, so you get 760. Right. So this is the end of the convolutional layers. So as I said, you have four filters in play. Number of actually, yeah, we're missing n. We're missing n here, which is the size of your input. So 5 things at play. So there's input size, there your filter size, your stride size, your padding size, and the number of filters. Because like here, if you use 10 filters, and you get if you use 10 filters, you get 10 dimensional output. Actually, your output will have a depth of 10. So 5 things that determine the size of your output: input size, filter size, number of filters, filter size, stride size, and the pad size. And based on this, you can calculate. And right, so there's yeah, right. Oh yeah, one more thing before we complete this chapter. One more thing is which is one-by-one convolution. Well, if we have time, we can talk about this in InceptionNet. I think InceptionNet is the one that came up with the word that actually heavily used one-by-one convolution for the first time. So one-by-one conv is, it might seem weird because we talked about so far 3 by 3, 5 by 5, 5 by 5, 7 by 7, but never 1 by 1. What is the point of 1 by 1? Well, actually, 1 by 1 is, handling 1 pixel at a time. If you use one by one convolution, then you're looking at one dimensional patch, one patch at a time, one patch, another patch, another patch, another patch, and you get the same dimensional output because you're not using. I mean, this doesn't even require padding, right? Because if you're using 3 by 3, you need 1 pad in order to preserve the space. But here you're using one by one conv on 1 by 1 patch, so there's no need to preserve the space anyway. It is automatically preserved anyway. So that is what is happening here. You're just looking at 1 pixel at a time. And simply, if you use, for example, if you have 1 by 1 conv with 32 filters of 1 by 1, then actually there's hidden 6 by 64 here. It should be 1 by 1 by 64 because it has 64 dimensional depth in your input. And then if you're using 32 filters, you will be getting 56 by 56 by 32. So your spatial structure doesn't change, but your depth changes. So what 1 by 1 conv can do is basically just, shrink or expand your depth without touching the space. So that is what 1 by 1 conv does. So you can keep that in mind. If you think your depth is too wide, too large, like 64, and you want to shrink it, you can simply use 1 by 1 conv and then shrink it down to 32. Or if you think your depth is too shallow, if depth is 6, you are not satisfied with 64 dimensional depth, you can use 1 by 1 conv filter with maybe 128 filters to blow it up to 128 depth without touching the spatial structure. And we talked about this, handling 1 pixel at a time. So we're going to skip this. Right. So as I said, we have 5 parts moving, and in the PyTorch, sorry about this. What happened here? Okay, sorry about this. Yeah. So if you look at the PyTorch CNN API, you can see that it accepts at least 4 things, which is number of filters, so kernel size, which is is it F here? We have F filter size or kernel size. We have the stride, we have the padding, and we have the output channels. Out channels being the number of number of filters here, output channels, and your in channel is actually determined by your inputs. So you can play around with these 4 things, to determine the size of your activation map. And there are a couple more things like dilation and groups and bias, but you can read about them if you're interested. So again, exactly like we said, if there are 5 things actually, 5 things, the first one goes here. So if there are 4 things that can determine the output of your activation map, then you can actually see a corresponding arguments here in your PyTorch. All right. Okay, so this was the end of the convolution, and I talked something about the pooling. So if you remember, there was like a convent value, conv plus value, and another conv plus value, and then there was pooling, right? So what is pooling? Pooling is actually a non-learnable. So there's no learnable parameters here. It's just deterministic. It's just an algorithm. So it's a very low weight operation for the whole low weight or low calculation thing in your whole component. What it does is basically people use it to shrink the size of your spatial structure. So if you have for example, let's say that your input dimension is like this. It's 224 by 64, and you can do a pooling operation to simply just reduce your spatial structure by half. So you can see here, 224 was shrunk down to 112, and your depth is preserved. So that's what's happening here. So typically we use it for downsampling, but you can actually do it for super sampling as well. Like if you wanted to increase by 448, you can also use pooling, but usually people use it for downsampling. So make the representation smaller and more manageable. So if you have like large activation maps, then you need it's like hard to handle. So you want to shrink it as much as possible, so your operations become faster. It is more compressed and all the kind of stuff. And your pooling operates on each activation map independently. So each activation map means each depth independently, like one depth at a time. So what does pooling do? It's very simple. Max pooling, all max pooling does is that for example, you can actually, there's a bit more parameters that you need to determine, which is the filter and stride. Again, filter and stride here. So if you're max pooling with 2x2 filters with stride 2, what happens is that you have 2x2 receptive field, and then you pick the maximum value out of these 4 values, which is 6, and then you stride by 2. So you stride by 2 pixels. You move on to the next 2x2. You pick the maximum value, which is 8. You get 8. Again, 3, and then 4. So that's it. It's 6, 8, 3, 4. So basically, what max pooling does is that looking at a determined small size patch, you take the strongest signal, being you assume that is the most important signal. You just disregard all the other rather irrelevant weak signals, and you only handle the strongest signals. So you're just extracting the most important things out of it. So that's max pooling. And there's another thing called mean pooling, and you can easily assume what it does is that mean pooling is simply just averaging of the given patches. So 1 by 1156, if you average them, you would get what is 13 divided by 4. So 13 divided by 4 here. 13 divided by 4. This is 15 plus 6 is 21 divided by 4. This is 8 divided by 4. This is, again, 8 divided by 4. So this is a bit more, mean pooling is a bit more like, forgiving, for example, to say. Like max pooling, it only cares about the strongest signal out of 4 pixels, right? Four values. But mean pooling just averages them out. So it considers all values or all information. But people usually use max pooling, actually. They don't use mean pooling as that often. Question. 풀링을 통해 인풋 데이터의 정보를 손실하는 것이 아닌가요? 그게 포인트예요. 일부러 손실을 시키는 거예요. 그러니까 일부러 손실을 시키도록 그 맥스 풀링을 이용을 하면은 이제 전체적인 이 뉴럴넷이 이제 손실이 있다는 걸 알기 때문에 이제 정말 중요한 정보만 최대한 뽑아내거든요. 뭐냐면은 이제 그 적자 생존을 하는 거잖아요. 지금 이제 이 중에서 가장 나는 강한 것만 택하겠다라고 하면은 필터들이 이제 정말로 진짜 중요한 것만 내보내게 되겠죠. 선택받기 위해서. 그렇기 때문에 이제 그걸 노리고 이제 맥스 풀링을 쓰는 겁니다. 그러니까 정말 중요한 엑기스만 짜내기 위해서. So the question is, if we're using max pooling, aren't we losing information? And so that was a great question, by the way. Great question. And actually, that is the point, because we are shedding unnecessary information. We're removing unnecessary information. Then the whole network will try to extract only the most important information in order to survive, right? So in order to pass the max pooling filter, you only want to extract or retain the most important features, most important signals. So that is what we are after. Question from 한소희. 컨브렐류 풀 구조에서 컨블 레이어에서도 디멘션이 줄어들고 풀링 레이어에서 디멘션이 줄어드는 건가요? 그렇죠. 근데 이제 컨블 레이어에서는 이제 패딩을 통해서 그 디멘션이 줄어드는 걸 방지할 수가 있는데, 왜냐면 컨블 레이어는 이제 디멘션을 줄이는 게 원래 목적이 아니잖아요. 그냥 이제 어떤 패치 3x3든 5x5든 이제 어쨌든 그 작은 네이버후드, 작은 어떤 그 한 번에 3x3이나 5x5의 그 작은 단위를 보고서 내가 이제 어떤 칼큘레이션을 하겠다는 게 있는 건데, 그러니까 이제 이 차원이 줄어드는 건 부차적인 거죠. 그래서 이제 패딩 같은 걸 통해서 이제 그걸 보완을 시켜줄 수 있는 건데, 풀링은 애초에 차원을 가지고 줄이려고 있는 거예요. 그러니까 이제 풀링이 진짜 차원을 줄이려고 있는 거고, 컨볼루션은 사실 차원 줄이는 거는 부차적이다. 이렇게 생각하시면 됩니다. All right. So the question was that, question from another student is that, so pooling also reduces the spatial structure, and also convolution also reduces the spatial structure. And is that correct? So the answer is that convolution, your spatial structure being shrunk by convolution is actually a side effect, because convolution is all convolution cares about is that you have a certain like assumption. Your input signal, your two-dimensional picture or input pixel is such that it is okay to look at only 3x3 patch at a time, because it has a local dependency. Local dependency meaning that only these 9 pixels have a interaction with each other. Again, and another 9 pixels has an interaction with each other. You don't assume that this pixel here and this pixel here has a direct relation. You don't assume that. If you assume that, then you would have to use a feed-forward neural network with fully connected neural networks. You don't. If you assume that everything is interacting with each other, but since you're assuming that your input picture has a local interaction, like this has interaction with this interaction with this, because you're assuming that kind of that kind of property of your input picture, you're using convolution. So convolution is all about local dependency and trying to capture the local dependency or local interaction. So that is the essence of convolution. This convolution 32x32 is shrinking to 28 or 28 by 28 is a side effect. So in order to prevent that from happening, you can use padding. Pooling on the other hand is all about shrinking dimensionality. So that is the whole, it's like converse of convolution. Convolution is all about convolving, and pooling is all about shrinking. Hopefully that I'm making that clear. Right. So, and fully connected layers usually come at the end in order to, shrink the size of your activation bit one more time, before you go to your classification layer. Right, summary. So summary is exactly this. So you have your conv value repeated n number of times, and n was at here, the n was 2, n was 2 in here, so n was 2, and then you have pooling operation, and then you repeat that some number of times again. So you'll repeat that 1, 2, 3 times, 1, 2, 3 times. So this was 3, and then you have some fully connected layers followed by ReLU, which is again some number of times. Usually it was 2 or 3 back in the VGGNet or ZFnet or AlexNet days, and then you have multi-class classification layer at the end, softmax. That's it. And yeah, there's one dimension. You can actually do one-dimensional convolution neural network as opposed to two-dimensional. So if you think about two-dimensional convolution, sliding your two-dimensional filter 3x3 across your input, you can assume there's a direct analogy. You have, in order to, when do you want to use one-dimensional convolution? It's when you have one-dimensional input. So you have one-dimensional input like this, like a time series or some time series, and you can just convolve your 3x1 filter across your one-dimensional input, like 3x1 here, and you're left with so if you have filter size 3 with stride 1, you have 5-dimensional output, unless you have a padding here. If filter size 3 stride 2, you would get 3-dimensional output, and that's it. So pretty simple. Question. 혹시 conv-ReLU 2번에 한 번에 풀링한 이유가 있는지? I'm not really sure. That's a good question, but it's just a hyperparameter. Some heuristics were involved, and I'm not really sure why though. You can do 3 convs and 1 pool, or one conv and 1 pool. So I guess people tried a lot of different variations and found 2 conv and 1 pool to work the best. Right, so 1D component can be used in, it can be used in document processing like NLP, and it has a pretty good performance actually, surprisingly. So if you have like word vectors, we'll learn word embeddings. So, but if you're already familiar with word embeddings, you can imagine what's happening here. If you have word embeddings like this, and you apply like a 3-dimensional filter, 3x1 dimensional filter, and like 10 of them, then you would get 10 dimensional, like, well, actually, I guess they're using 4-dimensional output here. So 4 filters, 4 filters of 1-dimensional convnet, then you would get, like here, and then basically it's the same. If you think about 2-dimensional convnet actually being a 3-dimensional thing, because it has filters inside. I mean, it has depth inside. So there's width. I mean, there's height and width and depth, right? So your 1-dimensional convnet will have only the width and depth, right? So your output structure will be 2-dimensional. Then finally you can just squeeze them and flatten them into 1-dimensional structure, and then get a final output. Like, is this like a category of a news article or something? Right, and if there's 1-dimensional convnet, 2-dimensional convnet, then there should be 3-dimensional convnet, and you can exactly imagine what it would be like. It is used for 3-dimensional structures, such as videos, which has 2-dimensional structure with time, or actual 3D images like CT scans or MRI scans, which has actual 3D structures. And if you want to process 3D structures like CT scans and try to do a segmentation or like classification or object detection, it would be nice to use 3D convnet. In 3D convnet, you need to actually move across your 3-dimensional structure as well. So there's height and width, and I'm not sure what L is, probably length, I guess, height and width and length. So your 3-dimensional filter or 3-dimensional kernel needs to move horizontally, vertically, and in depth as well. And of course, there would be actually the 4th dimension, which is the channel dimension, like R and G and B, right? So actually your filter needs to be also 4-dimensional, has to be a 4-dimensional filter. So you can imagine how involved this whole calculation would be, because you're now dealing with 4-dimensional structures. So there's a lot of calculation going on. So usually 3D components are very, very like computation heavy, and it requires a lot of time and memory actually. So I don't think people use 3D comp as often as 2D comps, even if you're using like 3-dimensional structures. Right, so training technique. So this is the end of the pool, and 1D, 2D, and 3D comes. So now we're moving on to the pool training technique. We're actually running out of time, unfortunately. So we need to talk about batch norm before we end. So normalization. So normalization is usually a good idea. So if we think about normalizing your input, just your input pixels, when you do a simple image processing, it is a usually good idea to normalize your input pixel values. So, and you normalize it, you either, min-max normalize or you z-normalize, z-normalize, which is basically assuming that your input value distribution follows a normal distribution, and you do this. You take the expectation away, you minus expectation divided by your standard deviation, right? So this is z-normalization. So everything is normalized to this map here, and so unit Gaussian distribution. So zero mean, unit variance. So if you do this, if you train your neural network with this kind of, after this, this kind of normalization, and then if your input distribution changes, for example, your training data is MNIST and then your test data is cipher 10. Well, actually, it's not a really good comparison because this is black and white images and this is actually RGB images. So this is not a good example. But for example, let's assume that your training data is something and then your testing data is something else. It has this different distribution. Then your normalization wouldn't no longer apply well, and your model will have a very poor performance, right? So machine learning models are usually vulnerable to a distribution shift. But this kind of distribution shift not only happens in the input level, but actually it happens during training. So this is actually inference stage, right? You train and then you test. So testing is called inference stages. So this kind of distribution shift is when it happens during the testing phase, but actually distribution shift also happens when you train the model during the training phase internally inside your layers. So that's what we're going to talk about now, internal distribution shift, or some people call it internal covariate shift. So layer one, so during training, your layer will have a certain output distribution, right? Because layer will have an activation map, and your activation map will have a certain distribution, and then that activation map will be plugged into your next layer as an input, right? Previous layer's output is next layer's input. So your previous layer's activation map is, plugged in, is acting as an input to the next layer, and your activation map will follow a certain distribution, right? And actually, well, I guess need to draw it manually. And so for example, when you train, like let's say that you're in your ith iteration during your training, your mini batch training or whatever, and during your ith iteration, your k-1th layer's activation map followed this distribution, and then your kth layer will be trained, will in the next layer, in the next step, will be adapting to this distribution, right? But after, when you do a back propagation, what happens is that your layer k-1th layer will change its activation map distribution according to the back propagation, because there will be your learnable parameter will have some changes, and then your activation map will change according to your learnable parameters. So for example, after a ith iteration to I plus 1th iteration, your activation map is now changing, is moved slightly to this distribution. Does layer K know that it changed? No. The problem is that because it's back propagation, your layer K doesn't know that your layer K distribution will change after I plus 1th training iteration. So that's where internal distribution shift is becoming a problem, because your next layer doesn't change that your previous layer's distribution, the output distribution changes according to your back propagation algorithm. So that is why your whole training your optimization process is inefficient. It takes a long time. It doesn't train well because of this phenomenon called internal distribution shift. So what do you want to do in this situation? The idea is that let's normalize your activation map values as well, just like you normalize your input pixel in the very first layer. If you have a lot of layers, this is your input layer, and you usually normalize your pixel values, right? Just like that, let's normalize your every single activation map as well, so that your next layer doesn't have to suffer this kind of internal distribution shift. So that is the gist of batch normalization, actually, in order to cope with internal distribution shift. So how do we do it? How do we do it? In the BatchNorm paper, they call it not internal distribution shift, but internal covariance shift. But it's the same thing. And they want to solve it. So how do we solve it? They use something called BatchNorm operation. So what does BatchNorm operation do? It basically simply just, what it does is it calculates, first of all, it normalizes your output activation map values. So it normalizes like this. So you have your output activation map, output value. And so assuming this is some k-1 layers. This is like in some layer this is happening. So this is that layer's output value or activation map value. You take the average of it. You take the expectation and you take the standard deviation and you take the minus mean and minus mean divided by the standard deviation, and you get a normalized output value, right? And you don't just use it as is, because if you normalize as is and then plug it into your next layer, it'll be a too harsh of a constraint. Basically what you're doing is you're saying that you want all your activation values in all layers to follow exactly this unique Gaussian distribution, which is actually unrealistic. It's too hard of a constraint. So what you do is you rescale it back to some value that is, friendly towards your next layer. So what it does is, you normalize your output value, and then you rescale it like this by multiplying your normalized value with some scalar value gamma, and then adding some scalar value beta. And those two, gamma and beta, are the learnable parameters of your BatchNorm. So your BatchNorm operation actually involves these two learnable parameters. So that's it. So you take the activation map, you normalize it, and then you rescale it back. So the whole thing is a bit normalized and more friendly towards your next layer, and the whole your optimization process is it goes way smoother now. Yeah, it's called scale and shift. So all good now? Hopefully all good. Right. So basically what it's saying is, we always want to have the consistent distribution after a certain layer, like not like this, like after ith iteration, I plus iteration, I plus 1th iteration, I plus 2th iteration, not like this. Like every single time we want the output of the k-1 layer to follow this distribution, then layer k would have a much easier time just adapting to this and then trying to optimize its own parameter so as to maximize or so as to minimize the final loss function, right? So that's the whole gist of it. Right, so if you try to visualize what happens in batch normalization is that here, so the important thing is that when taking the mean of your average of your activation value or your output value, you take the average across your samples in your mini batch. So that is why it's called batch normalization, right? So what batch normalization is that you don't want your output to change batch after another batch, right? You want your normalizations to stay stable across all batches, and that's why you normalize. Or that's why you take the average across the batch dimension. So here it's taking the across the batch dimension n. So across the batch, and you leave the dimensions alone. So your output of your normalized value is actually is the same as n by d. So if you have an n by d input, then your normalized x hat before that goes on to y hat, which is a scale and shifted. Before that, your x hat has the same shape as n by d, because your mu j, which is the average value, is specific for each dimension. So j is the dimension index. So it's specific for each dimension. There's mu1, there's mu2, there's mu3, and corresponding sigma1, delta 1. Oh, actually, this is sigma 1, sigma 2, sigma 3 for each dimension, and that is why your normalized value is specific for each dimension as well. Each dimension. Right. So hopefully this is clear. The gist is that your average is done across the batch dimension, and Actually, that's the problem because, actually, before we move on, we already talked about this. So what if zero mean univariance is too hard of a constraint? Like I said, that is why we have a scale and shift here, scale and shift. So we're learning this gamma and beta. Will actually make it a bit more, give the whole thing a bit more freedom to move around. And as it says here, if gamma is the same as this sigma here, and beta is the same as this mu here, then it is actually doing just reverse engine, just doing nothing at all. It's just the whole thing at the same time. You end at where you started, but usually this doesn't happen. So it's just theoretical analysis, right? Yeah, the important thing is here, because your estimates, because you're taking the average across your batch dimension, right? Your mini batch dimension. So your estimates depend on mini batch. And the problem is that you can't do this at test time because you don't train. I mean, training is done by mini batch, but your inference can be done at one sample at a time. You just take one sample and then do an inference. You take another sample and then inference. You don't always take mini batch of test samples at a time, right? Because that is not guaranteed. So that is the problem here, because in order to normalize, in order to take the normal, in order to normalize your value and then scale shift, actually you need these two values, mu and sigma. And in order to do that, you need to have a mini batch. If you don't have a mini batch at your test time, you can't calculate mu and sigma. You can't normalize, and the whole thing breaks down. So that's the problem with batch normalization. There's a discrepancy between when you're training and when you're testing. So this whole thing breaks down when you're testing. So that is why you actually need to keep the running average during training. As you train, as you train like hundreds or thousands of iterations, you keep the running average of mu's and sigmas across all mini batches, and then you save them, and then you load them when you test, and then you recycle those values, mu's and sigmas, those values when you test. So that's kind of the drawback of BatchNorm, because there's a discrepancy between training and testing. So you have to keep the mu's and sigmas that you calculated during training around. You need to save them and then reload them during test time. And that is actually a source of a lot of bugs, actually. Back in 2015, 2014, 2015, when BatchNorm first came out, this used to be like a source of a lot of bugs. Question from 이민승. 레이어 통과 전에 배치놈을 하고 레이어 통과하고 다시 오리지널 스케일 돌려놓는 건가요? 아닙니다. 레이어 통과한 후에 레이어 통과 다음에 레이어 지금 보시면은 여기서 일어나죠. 레이어 통과 다음에 액티베이션 맵, 그러니까 이제 아웃풋 쪽에서 레이어 통과 후에 아웃풋을 가지고 배치놈을 해서 노멀라이제이션 하고 리스케일 한 다음에 다음 레이어로 보내주는 겁니다. 그러니까 레이어랑 레이어 사이에서 일어나는 일이에요, 배치놈은. Question from 신재욱. 처음 2016년도에 배치 노멀라이제이션 발표됐을 때 코베리어 시프트를 제거하기 때문에 성능 높인다고 발표되었는데 2018년도 배치놈이 코베리어 시프트를 제거하지 못한다는 수식적 실험적 증명을 해서 오브젝트 펑션의 노션 스페이스를 스무딩하기 때문에 빨리 설명 답변 공부했습니다. 네, 추가 후에도 이제 굉장히 많은 이제 분석들이 있었을 거고, 막 배치놈 저자가 배치놈 2도 만들고 막 그랬는데, 이제 배치놈이 요즘은 그렇게 많이 사용되는지 모르겠어요. 왜냐하면 이제 요즘은 다 트랜스포머만 사용을 하기 때문에 이제 CNN도 사용하지 않고, 근데 트랜스포머 안에 또 레이어놈이라는 게 있잖아요. 이제 배치놈을 사용하지 않는, 이제 대부분은 배치놈을 사용하지 않는 세상이 왔죠. 그래서 좋은 지적입니다. Right, so there's a direct message to me that the reason that BatchNorm actually performs better is not because it copes with Fourier shift, but for some other reason. But there were a lot of follow-up analysis of what BatchNorm actually does and its relationship with dropouts and all those early techniques. And these days, as I said in Korean, BatchNorms are not as oftenly used as before, because these days a lot of people just focus on using transformers, and transformers don't use BatchNorm, they use layer norms. So we'll talk about layer norms now. Right, we talked about the source of bug being this having to keep around the mu's and sigmas. Also, another thing of debate back in the day is where is the best place to locate to put BatchNorm? Is it before the nonlinear activation function or after the nonlinear activation function? And usually, I think people just use it before the activation function. But again, this is just another designer's choice. Yeah, again, behaves differently during training and testing. This is a very common source of bugs, as I said. Yeah. So batch normalization for convolution. So this is batch norm for like this. Oh, sorry. This figure here is just batch norm for feed for a neural network. You have just different samples per layer. Different samples per row, and each dimension is just different features, right? But in convolutional, you have 2 by 2 by 3, right? 2 by 2 by. I'm sorry, not 2 by, like height and width and RGB here. So what happens then? How do you apply batch norm in two-dimensional structure like in convolutional? So here, in N by D, which is a fully connected network, what you do is you take the average across the batch, so your mu and sigma will look like this 1 by D. In convolutional, you take the average across N and H and W all at the same time. So spatial structure and your batch structure is all collapsed into just ones, and all you're left with just channels. So you have different mu's and sigmas per each channel, not per each width or not per each height, only the channel. So your only channel survives it. So that's what happens in batch norm in convolutional. Layer norm is something different. Layer norms are it's like an antithesis of batch norm, because batch norm takes average across the batch dimension. Layer norm goes the other way around. Layer norm actually takes average across the dimensions and it leaves the batch dimension alone. So that's what's happening here. If batch norm takes average across batch, layer norm takes an average across the dimensions, and that's how it normalizes. And that is why it has the same behavior as train and test, because it doesn't care about the batch size or anything. It only cares about the dimensions, and your dimensions don't change. Your structure doesn't change, right? So it has the same behavior during test, training, and test. So it's way more easier to handle. There's a lot of bugs, and it also can be used in recurrent neural networks. Actually, layer norm actually came out to be kind of specifically to be used in RNNs back in like 2015 or 2016, and you can see that average done across the D, which is the depth or feature channel. And instance normalization is a bit more recent now. So if this is batch norm, you take average across the batch size, your height and width, and only the channel survives. Instance normalization is actually, it doesn't take the average across the batch. It only takes the average across height and width, and that's it. So it only, it's a very convolutional neural network specific normalization, instance normalization. So it is used in like style GANs and that kind of stuff, style transfer and that kind of stuff. So which means that you only care about you don't care about the spatial dimensions. You only care about the channels, and you leave the batch norms, you leave the batch dimension alone. So you only care about one sample at a time, because the ends are intact. So that is why it's called instance normalization. So here a bit of like a three-dimensional depiction of what's happening in batch norm, layer norm, and instance norm. And because it should be a four-dimensional structure, because there's height and width, but we can't draw four-dimensional structure. So height and width, the spatial structure, is actually collapsed into one axis here. So there's channel axis, there's batch axis, there's height spatial axis. And in batch norm, what happens is that only the channel axis survives, only the channel, because you take average across the batch, you take the average across the height spatial structure, and only the channel survives. So there's one color per channel here, as opposed to that layer norm. It leaves the batch axis alone. It only collapses the height and channel. So you have one blue thing per each instance, per each sample in your mini batch. And instance norm, it doesn't collapse. It also collapses the channel as well. So you only have the height and width. I'm sorry, actually. Yeah, I'm sorry. You only collapse. You only take the average across the spatial axis. So your N and C's are intact. So that is why you have one blue thing at each end and each channel at the same time. Right. So there are different norms, and there's like adaptive instance norms and all like more advanced stuff. But instance norms are usually used in style transfers and domain transfers and like style again as well. So in order to take the styles out and only take the semantics, and then you draw it in a different style and that kind of stuff. BatchNorm is used for like CNNs usually, and layer norms are heavily used in transformer these days. So you can take this image and then keep this in mind, what really happens inside. Right, the final thing. So we are already 4 minutes over, so I'll just go over the dropout real quick and then finish. So dropout is a very simple technique that was developed back in 2012, I think, 2012 or 2013. I think it was first proposed in AlexNet actually, and it was a hidden, like a very, very important technique to make the model generalize really generalize better to the test environment. So the whole gist is that you set certain number of hidden nodes to 0, just certain proportion, certain probably like 10%, 20, 15%, 20%, some number of hidden nodes. For example, if your hidden node is 5 and you take 20% out, it means that you take one, on average, you take one node out of the picture. So here is like 2 nodes are canceled, 3 nodes are canceled, 2 nodes are canceled, and you're left with only smaller number of nodes activated at all times, and it needs to somehow learn to adapt to this very hostile situation. So that is why it is generalizing better, because it needs to use kind of like autoencoder actually, because if you think about autoencoder, it extracts and compresses the most important information of your data set, right? It's the same thing. If you're constrained to use smaller amount of information channel, then you are bound to use the most important feature at a time. And since you're canceling different hidden features, or different filters one at a time, each filter needs to adapt differently. So that is why it generalizes so well. So if you're using dropout in Confident, what you can do is you can actually cancel out certain portion of your activation map. So certain scalar, like small proportions, small ratio of your activation map values, or you can actually do like this. You can actually entirely cancel out your activation map. So if you have 6 activation maps, you can cancel out maybe 2 at a time, randomly 2 at a time. The important thing is that your cancellation has to be random, like sometimes here, sometimes here, sometimes here, or as randomly as possible. So there, as you said, as I've seen here, dropout and Confident can be implemented in 2 different ways. But I think people just actually, I'm not really sure what. I think this is more common because they cancel out the filters actually. Like sometimes I use filter if you have like 8 filters. Sometimes you cancel out 1. Sometimes you cancel out 2, 4. Sometimes you cancel out 1, 5. Sometimes you cancel out 2, 4, 6. Something like that. So you canceling out a filter is basically canceling out an activation map. Right. So this is it. So we talked about norms and dropouts, and unfortunately, due to time constraint, I can't go to all different CNN architectures. If you have time, you can go through them, one by one. 2012 is the birth of AI, birth of deep learning with AlexNet, and then came out ZFNet, VGGNet, Google InceptionNet, ResNet, and then all different kind of WideNet and SqueezeNet and EfficientNet, DenseNet. They all came after that. So you can actually take a look at them, like how the what was the main idea of like early convnets like AlexNet, VGGNet, InceptionNet, ResNet, especially ResNet. ResNet is a very important concept. Actually, the whole idea of residual connection survives until today, 8 years later. So it's a very important concept. So please go ahead and maybe if you have time, please go ahead and take a quick look at the whole slide. Right. So I think this is it. Before we end, any question? Sorry for being a bit going overboard. Wow, we're 8 minutes actually over. So question, R는 타임 디멘션인데 노멀라이제이션 어떻게 처리되나요? 타임 디멘션이 있지만 이제 그 레이어 어차피 매 타임 스텝마다 사용되는 레이어는 똑같지 않아요. 어차피 똑같은 그 러너블 파라미터를 재사용하는 거기 때문에 이제 거기다가 레이어 노멀 껴 넣어주는 겁니다. 이제 레이어 노멀리제이션 논문을 한번 읽어보시면 금방 이해되실 거예요. 논문 이름 자체가 레이어 노멀리제이션이거든요. 그래서 그것도 제프리 힌튼 교수님이랑 지미바라는 그 당시에 그 학생이 이제 쓴 논문인데 그 채널 디멘션 그러니까 이제 채널 쪽으로만 이 노멀라이제이션을 하기 때문에 이제 그게 굉장히 여기저기서 많이 쓰일 수가 있습니다. 네. Okay, so right. So if you have any question, please post them on Classroom, and then I'll see you. So next week will be actually will be the midterm week. So you can focus on other class midterms also as well as the project number 1 in our class. So next week is an off week, and then I'll see you guys the week after that with a word embedding, a subword embedding. This Thursday, you guys will go over the implementation of CNN, very simple CNN. It's not the large ones, though. Simple CNN is also the TAs will announce the details, the specs of project number 1, and some skeleton codes and how you can submit your materials, your deliverables, and all that kind of stuff. So please attend this week's practice session. All right, thank you very much, and I'll see you guys. Good luck with your midterm week, and I'll see you guys the week after. Thank you very much. Bye-bye. 네, 감사합니다.